your tutor Pragya some PMRF at Department of Chemistry, IT Khan. So in last class, what we have studied, we studied how we can measure this delta U and delta H. So we can measure delta U using this your warm calorimeter and delta H by using this coffee cup calorimeter. Okay. And after that, we solved the problem, and this was the problem we solved. Okay. After that, we were studying the applications. So in application, what we studied the calculation of heat of formation. Okay, so we can calculate the heat of formation if we know the standard enthalpy of combustion. Okay, so using that we can easily calculate the heat of formation. Coming to the next application. So the next application is the calculation of calorific peak value of food and fuels. Right? The okay. The calorific value is defined as the amount of heat produced in calories when 1 gram of a substance is completely burned. So, if you burn 1 gram of substance, then the amount of heat produced in calories, we call it as a calorific value. Okay, and its SI unit is joule per kg. Okay, so the amount of heat that will be in joule. Okay, when you burn 1 gram of substance, okay, so it can be gram. Okay, so the amount of heat produced when you burn 1 gram of substance, that is called like as a calorific value. Okay, so it can be joule per gram or it can also be joule per. Okay, this is what we call as a calorific value. Okay, it is written that it is usually expressed in calories. Okay, so the cake can also be have the unit of calories. Okay, so if we are taking it in calories, then it will be calories per gram. The amount of heat produced in calories we are taking in it in calories and for per gram. So if we are taking calories per gram, then we will call it a calorific value. So this will be calories per gram, which is nothing but your calorific value. Okay. Heat of solution. Okay. Next is your heat of solution. A heat changes are usually observed when a substance is dissolved in a solid. Okay. Let us say this is a beaker. Okay. And it has a solvent. Let's say DCM is here. DCM is basically a dichloromethyl solute. Okay. So when you dissolve a substance, let us say we are dissolving any organic compound. Okay. So in that case, what will happen? They will produce heat. Okay. Once you dissolve this organic compound in the solvent, it will produce heat. So heat changes are usually observed when a substance is dissolved in a solvent. And then this heat of solution, okay, is defined as the change in enthalpy when 1 mole of a substance is dissolved in a specific quantity of solvent at a given temperature. Okay, let us say you are taking 1 mole of this organic compound. Okay, now its mole is fixed. Okay, you are taking 1 mole of this organic compound and the quantity of the solvents. Let's say you are taking 5 ml of this solvent. Okay, the quantity of the solvent and the temperature is, let us say you are taking it at a room temperature, that is 25 degrees Celsius. Okay, so when 1 mole of substance, that is you are dissolving your 1 mole of this organic compound in a specified quantity of solvent, that is in 5 ml of this young at a given temperature, that is at 25 degrees Celsius. Then the heat of solution will be defined as the change in enthalpy. Okay. So this is what is called as heat of solution. That is the heat changes observed when a substance is observed it dissolved in a solvent. Okay, when you dissolve a solvent, dissolve a substance in a solvent, there will be change in the heat, and that change in the heat is defined as the change in enthalpy when you dissolve 1 mole of the substance in a specified quantity of a solvent and at a given temperature. Next one is the calculation of the heat of neutralization. Calculation of heat of neutralization. The heat of neutralization is defined as the change in enthalpy, okay, when 1 gram equivalent of an acid is completely neutralized by 1 gram equivalent of a base, or vice versa in dilute solid. So what is heat of neutralization? When it is the enthalpy change, okay? How is enthalpy change is occurring? So because here neutralization is happening. Okay, what is neutralization? When your 1 gram equivalent of an acid is getting neutralized by 1 gram equivalent of base, then this is called as a heat of this is called neutralization, and the heat generated will be called as the heat of neutralization. That is the changing enthalpy. Okay, so it is the change in enthalpy when you neutralize 1 gram equivalent of acid with 1 gram equivalent of base, or vice versa in a dilute solution. So this is what your enthalpy of heat of neutralization. The heat of neutralization of a strong acid and a strong base is around minus 57.32 kilo. Irrespective of the nature of acid or base used, which is evident from the below mentioned examples. Okay. Now I will take some examples and show you why they have said this statement, why they have made this statement. So what they are saying that the heat of neutralization of a strong acid and a strong base. Okay, so let us say you are taking a strong base and you are neutralizing it with a strong base. Okay, in that case, the heat of neutralization will be minus 57.32 EU. Yes. Irrespective of the nature of acid or base you are in. Okay, so this is very important that irrespective of the nature of base or acid you are using. Okay, so this is very important. So let us see how. Okay. Let us take the first example. You are taking HCl. HCl is your acid, and you are taking sodium hydroxide, which is your base. Now you are neutralizing your HCl with sodium hydroxide, that is acid with base. Okay, so what will happen? Acid plus base, your salt and water will form. Okay, what salt will form? Na and Cl. So it will become NaCl and your water. Okay. Nice. So here your H plus will react with OH minus and it will produce water, and your NH plus ion will react with your Cl minus ion and it will form NaCl, that is salt. Okay. It is found that enthalpy change of this reaction, that is heat of neutralization of this reaction, is minus 57.32 kilojoule. Okay. Let us take another example. This one is first example. Let us take another example. This one is HCl. Sorry. Again, you are neutralizing HCl with KOH. Okay. So what will happen? Here it will form HCl and water. Okay. So here same thing. You are neutralizing your HCl with potassium hydroxide. That is base. Here it is acid. Base. Here it is your salt and is water. Okay. So here this HCl is your acid, and here you have changed the base. So base here is your potassium hydroxide, that is COH, and after neutralization they will form potassium chloride, that is salt and water. Okay. And it has been found that the heat of neutralization in this case is minus 57.32 kilojoule. Again, here we are getting the heat of neutralization as minus 57.32 kilojoule. Let us take now another example. Hello. So we are doing all this to see why they have made this statement. Okay. Let us take another example. Here we are changing the acid now. Let us take another acid, that is nitric acid. HNO3 is your nitric acid, and you are neutralizing it with base. Okay. So what will it form? Your H plus will react with OH minus and it will form water. And your K plus will react with your NO3 minus and it will form KNO3. Okay. It will be KNO3, potassium nitrate. Okay. And the heat of formation, similarly, heat of neutralization was found to be minus 57.32 kilojoule. But that is minus 57.32 kilojoule. Same. Okay. Same as in this cases. Okay. Now let us take the last example. That is K2SO. Now let us take sulfuric acid. It's a very strong acid, right? And we are neutralizing it with base. That is potassium hydroxide. Okay. So here 2H positive is there. Then 2H positive will need 2 moles of hydroxide ion. So what will they produce? 2 moles of water. And here your K plus and SO4 minus will form K2SO4. Yeah. Because your SO4 is 2 minus and here you have 2K plus. So in combination, we have 2K plus and SO4 2 minus. So what will they form? K2SO4. Okay. K2SO4 aqueous. And your water. So this is what we get as a product. Okay. And again the heat of neutralization in this case was found to be minus 57.32 kilojoule. So this was the reason. Okay. So why we are getting all these values same? So here, if you see what exactly is happening, here your H plus from H plus and here OH minus. Okay. They are reacting to form water. Okay. So the reason for this can be explained on the basis of Arrhenius theory of acids and bases, which states that strong acids and strong bases. So all these are strong acids. Your sulfuric acid, nitric acid, hydrochloric acid, all these are strong acids. Similarly, your sodium hydroxide and potassium hydroxide, they are strong bases. So they are stating that for strong acids and strong bases, they completely ionize in aqueous solution. Okay, so in aqueous solution, they will form If HCl is there, in aqueous solution, they will form H plus, Cl minus aqueous. Okay? So they completely ionize. That means they will be in the form of H plus and Cl minus in aqueous solution to produce H plus and OH minus. Acid will produce H plus and your base, that is let's say NaOH, they will produce Na plus and OH minus. Okay? So this is the reason why you are getting all the heat of neutralization same, because what is happening? Only your H plus that is reacting with the OH minus. Okay, so that means the reason for this can be explained on the basis of RNA theory of acids and bases, which states that for the strong base acid, this is very important. This is only for the strong acid and strong bases that completely ionize in the aqueous solution to produce H plus and OH minus ions respectively. Okay, and it can be expressed as H plus aqueous is reacting with OH minus aqueous to produce your water liquid. Okay, so and the enthalpy change of this reaction is minus 57.32 kJ. Okay, so basically what is happening? Your S plus, and there is a reaction between your S plus and OH minus ions in the aqueous solution, which is leading to the formation of your water, and that's why your enthalpy of the reaction, all these reactions is enthalpy of your heat of neutralization of all these reactions is are same. Okay, so this is why they made this statement. Okay, so now we know that the heat of neutralization for the strong acid and the strong base is minus 57.32 kJ. Okay, so this is applicable for the strong acid and strong base cases. Now let us move to the next slide. So what is molar heat of fusion? The molar heat of fusion is defined as the change in enthalpy. Okay, so basically we are studying the application of the enthalpy changes. So if there is a change in enthalpy, then 1 mole of solid substance is converted into the liquid state at its melting point. Okay, let us take an example. Okay. Now let's say you have a solid substance. Okay. It's a solid substance and you have defined it is 1 mole. Now at melting point, okay, let's say your T is your melting point. If this is the case, then your solid will be converted into the liquid. Let's say this is a liquid. Okay. Your solid will get converted into liquid at your melting temperature. If that is the case, then here your enthalpy will change. Your enthalpy will change. And this change in enthalpy, when your 1 mole of a solid substance is getting converted into your liquid state at its melting point, this is called as molar heat of fusion. Okay, so this change in enthalpy has a name and we call it as a molar heat of fusion. Fusion, why? Because your solid is getting converted into the liquid. Heat, because there is a change in enthalpy, and molar because we are taking a particular mole of a substance. Okay, so this is what the change in enthalpy is, the molar heat of fusion in this case. So let us take another example. The heat of fusion of ice can be represented as the heat of fusion of ice. Let's say you have ice, okay, and your ice is getting converted into your water that is liquid, and it happens at what temperature? 0 degrees. Okay. So, what is happening? Water, which is in your solid state, is getting converted to the water that is in liquid state. Okay. So, at 273 Kelvin temperature. So, the enthalpy change in this case will be called as molar heat of fusion, okay, which is equal to plus of 5.98 kilo. And here, plus sign, you already know it denotes that it is an endothermic reaction. That means in order to go from your solid, that is ice, to water that is in liquid state, you will have to apply, provide this much of energy in order to get further in your liquid state. Okay. So this is what is the molar heat of fusion, which is the change in enthalpy when one mole of a solid will be converted into its liquid state. When you give its melting point, then that enthalpy will be called as the enthalpy change will be called as the molar rate of fusion. Okay, so this is the example, okay, where your ice is getting converted into water at 273 Kelvin, and the heat of fusion for that is 5.98 Kelvin. Now let us move to the what is molar heat of vaporization. So the molar heat of vaporization is defined as, here again, the change in enthalpy when one mole of liquid is converted into vapor state at its volume. Okay, so here you are converting liquid to vapor. Let's say you have a container and you have water. Okay. Now you are heating it at 673 Kelvin, that is 100 degrees Celsius. Okay. Now what will happen? Evaporation will start. Evaporation will start. Your water will get start reducing in liquid state and it will form vapors, which is watery gaseous state. Okay. So what we are doing? We are changing it. We are basically what is happening over here. One mole of liquid is getting converted into its vapor state at its boiling point. Okay? So this will happen when we do the boiling point. So this process involves a change in enthalpy. This process in which you are changing a substance from its liquid state to its vapor state. So this process involves enthalpy change. If this is the case, then this enthalpy change is called as the molar heat of vaporization. So this enthalpy change is called as the molar heat of vaporization. Okay. Let us take an example. So here the heat of vaporization of water can be represented as, So what you are doing, you are making your water, which is in liquid state, to uh, in and you are vaporizing it. That is, you are making it in vapor form. That is gaseous state. So let us write the equation for that. Water, which will be in your liquid state. Okay, now you are giving temperature, that is 100 degrees Celsius, that is scale 73 Kelvin, and you are converting it to gases. That is its vapor state. Okay, so this is called heat of vaporization. So this is called as molar heat of vaporization, and it is written as delta H VAP, that is vaporization, and its value is plus of 40.626 Kelvin. Okay, so see, you can clearly see that in order to get your water vapor, you will have to provide the energy. Okay, so because this is an plus sign denotes an endothermic reaction. So here you will have to provide energy in order to uh, see this change. Okay, so in order to observe this change, or in order to get your water in the vapor phase, you will have to provide this much of energy to. Okay, so this is the case, and the here in this much enthalpy change is called as the molar heat of circulation. So these are the terms we use. Okay, so you must be familiar with this. Okay, so in case you are going from solid to liquid, we call it heat of fusion, and if we go from liquid to gas, we call it vaporization. And what will happen uh, if your solid is going to your direct gaseous phase? In that case, we call it heat of sublimation. Okay, let us study heat of the sublimation. So, what is molar heat of sublimation? So, sublimation is a process when a solid changes, as mentioned earlier, directly into its vapor state. Okay, so we are going directly from solid state. Okay, uh, surpassing, we are not going through it from solid to liquid, then gas. We are going directly from solid to its vapor state. Okay, from solid to vapor state. So in case, so here in this case, we call it molar heat of sublimation. That is the change in enthalpy when one mole of a solid is directly converted into its vapor state at its sublimation temperature. Okay, so your solid state will be converted into your vapor state, and with that temperature is called as a sublimation temperature. Okay, so you must remember that what these temperatures are called. So in case of liquid to vapor, we call it boiling point. In case of solid to liquid, we call it melting point. And in case of solid to gas, we call it sublimation temperature. Okay, so these are the temperatures, and we call them like this. Okay? So the molar rate of sublimation is defined as the change in enthalpy when one mole of solid is directly converted into the vapor state at its sublimation temperature. Okay? So let us take an example. The heat of sublimation of iodine is represented as okay? The heat of sublimation of iodine. That is, firstly, your iodine was in solid state. Okay? Now, we provide the sublimation temperature, and its sublimation temperature is T73 Kelvin. Okay. Now, if you give this temperature, then your iodine will directly be converted into your vapor state. That is, iodine in solid state will be converted into iodine in vapor state. And what we call it? We call it heat of molar heat of sublimation. Okay. So here, as you will denote sublimation, and it is plus 62.42 kilojoule. Yes, if I'm right. I'll write it again 1 second because I have to write many things. Yeah. Okay. Just I'll write it quickly. That is your iodine, which is in a solid case, will get converted with iodine in your vapor phase if you get the rate of sublimation is plus 62.4. So this is the equation, that is just iodine is getting converted to from its solid state to its vapor state directly. Okay, and we call it rate of molar rate of sublimation, which is plus 62.4 degrees. That means we will have to provide energy because it is an endothermic reaction. And another example of this sublimation is the solid will solid CO2 to gas at atmospheric pressure at very low temperatures. So another example of this is where uh, so another example of this sublimation process is when your solid your CO2 is in solid state gets converted into CO2 in your gaseous state. Okay. So this is another example of sublimation where your solid is getting directly converted to gas. And this happens at atmospheric pressure. This happens at because we have to provide particular temperature, okay? Sublimation temperature. So this happens at very low temperatures. Okay, the temperature should be very low and at atmospheric pressure. Okay, so this is important that it happens at very low temperature. Carbon dioxide solid to carbon dioxide gas. Yeah. So this was another example. Okay, so molar rate of sublimation is what you have studied in this slide. Now let us move to the next slide, which is okay. So what is heat of transition? Transition with from transition, you can basically understand that something is changing. Okay. So what is that heat which is changing in this case? Okay. So here the change in enthalpy when one mole of an element changes from its one electropic form to another. Okay. So the change in enthalpy when let us say you are taking an element. Okay, let us say you are taking carbon. Okay, and it is in diamond form. Okay, so it it's in it is in its diamond form. Okay, now if your carbon which is in your diamond form is getting converted into carbon which is your graphite form. Okay, so in this case what is happening? Your one mole of an element that is carbon here changes from its one electropic form to another. That is, it is changing from diamond, carbon, graphite. So in this case, enthalpy will change again. So the enthalpy change in this case is called as the heat of transition. Okay, so the heat of transition is the enthalpy change in this case. Okay, when what when an element changes from its one form to another form. Okay, so the example was your carbon which is in diamond form is getting converted to your carbon which is in graphite form. So not. And delta H calculated for this reaction, that is molar heat of transition, which is equal to plus of 13.81 kilojoule. Okay, again, this is an endothermic reaction. Okay, so this will be called as the heat of transition. Okay, where your element is changing from its one form to another form. Similarly, the allotropic transition in sulfur and phosphorus is also the heat of transition. For sulfur monoclinic. Okay, so it is one of its form of sulfur. It changes from sulfur monoclinic to sulfur rhombic. Right. So its one allotropic form is monoclinic and another allotropic form is rhombic. Then, if it changes from one form to another, we call it heat of transition, which is equal to minus of 0.067 kilojoule. What does it mean? So here you don't need to provide any energy. Okay, so this is an exothermic reaction. This can happen without providing any kind of energy. Okay, that means your rhombic form is more stable. Okay, so this happens. Okay, that means your S in your rhombic form is more stable than your monoclinic form. That's why your heat of transition is your negative. Okay, so that means you will not have to provide any energy. Okay. Another example is the phosphorus. So this was example one. So example, and this one is example. Another example is of your white, when your white phosphorus gets converted to your red phosphorus. You know white and red phosphorus? Okay, so if your white phosphorus is getting converted into your red phosphorus, this is also the, there will be change in entropy that will be called as heat of transition, and it is equal to minus of 4.301 equal. Okay, what does it mean? That reaction is your, this process is your exothermic. Okay. Okay. Now we have enough examples. We have read enough examples of heat of transitions. Now let us move and study what is Hayes law at constant, Hayes law of constant heat substitution. So what is Hayes law? So Hayes law is this Hayes law of constant heat summation. Okay, let us see what is Hayes. This generalization is known as Hayes law and is stated as the enthalpy change of a reaction either at constant volume or at constant pressure is the same. Okay, that means the enthalpy change, if a reaction is happening at a constant volume or at a constant pressure, then the enthalpy change of that reaction will be same whether it takes place in a single state or it takes place in a multiple states, provided that the initial and final states are same. Okay, so what His law says? So it states that, let's say you have a reaction. Okay, a reaction is happening at a constant volume and a constant. So if that is the case, so whether this reaction happens in a single state or it can go via multiple state to form the okay, but the product will be same. Okay, so let us say A is going to be, A is its initial state and B is its final state. Okay, and let's say delta H is the enthalpy change here. Right. Your delta H is your enthalpy change in this case. Okay. Let us say this reaction, outputs the around. This A is going to form another analytical form that is A dash. Then it undergoes a different reaction and forms A double dash. Okay. And then finally it forms B. What is happening over here? So instead of directly going from A to your B, no. Here A is going through many steps. Okay, here A is following two steps in which first it is changing from A to A dash, and in the second process it is changing itself from A dash to A double dash, and finally it is forming B. That is initially, and this is final. Okay. So if you calculate delta H for this reaction, that is A to B, then see the initial and final state. The condition is that the initial and the final state are same. Then this is applied. So here A was its initial state and B was its final state. So here they are saying that the enthalpy change of reaction will be same. So here in this case, if you are let's say the enthalpy change for this reaction, that is delta from delta A to A dash was H1. From A dash to A double dash, it was S2. From A double dash to B, it was S. Okay. If delta H, that is delta H1, delta H2, plus delta H3, this will be the enthalpy change for this reaction, like from this to this to this. Okay. So they are saying that this, if you add this, then the enthalpy change you get will be same as that in your previous. Okay, because here the initial and final state are same. So it doesn't matter you are going from going to its final state from its initial state following only a single state, or this is a single state, or multiple state. This one is what multiple state reaction. Okay, so this is what they are saying. That this means this delta H and this delta H will be same. Okay, so here now you can clearly understand that the enthalpy change of the reaction either at constant volume or at constant pressure is the same whether it takes place in a single state or multiple states, provided that the initial and final states are same. That is, initial state and final states are in this cases are same. Okay, this is what is the statement of the case law. Okay. Now let us study the application of the case law. So Hess law can be applied to calculate enthalpies of reaction that are difficult to measure. So this is the application of Hess law, which says that we can calculate the enthalpy of reaction which are difficult to measure. For example, it is very difficult to measure the heat of combustion of graphite. So it is difficult to measure the heat of combustion of graphite. So what will the combustion of graphite will produce? Carbon monoxide. Okay. So the heat of combustion of graphite will give pure carbon monoxide. It is difficult to measure. So what we can do? We can, however, the enthalpy for the oxidation of graphite to CO2 and CO to CO2 can easily be measured. However, enthalpy for the oxidation of graphite, okay, you are you can calculate for the oxidation of graphite using graphite from here. First, oxidation of graphite. How one thing? Okay. So the oxidation of graphite is on CO2. What's it? This is known. Enthalpy for this reaction is known. Let us say delta S. One is the enthalpy for this reaction. This is known. And enthalpy for oxidation of CO to CO2 is also known. Let's say your CO reacts with oxygen and it forms, it will form CO2 gas. Okay, your CO gas will react with your oxygen gas and it will form CO2 gas. Okay, one mole of oxygen from here. Okay, and it will react with CO and will form CO2 gas. And enthalpy of this reaction is also, let's say delta S3, it is also. If we know the enthalpy of this reaction, then what Tesla says that we can easily calculate the heat of combustion of graphite using this equation. So for this conversion, the heat of combustion values, okay, so the heat of combustion values which we know, these are given, okay, that is minus 393.5 kilojoule. It can be easily be measured, okay. So here for the graphite, oxidation of graphite to CO2, it is minus 393.5 kilojoule. And for oxidation of carbon monoxide to CO2, it is minus 283.5 respectively. So it says that from this data, the enthalpy of combustion of graphite is here. Okay, so the enthalpy of combustion, that is the heat of combustion of graphite to CO can be calculated. Okay, so this is what the beauty of this law, that we can, for because it was very difficult to measure. Okay, now we can measure it using the Higgs law. Okay, if we know these values, okay, it can easily be measured. Okay, now let us write the reaction involved in this process. Okay, so I'll write here the reaction involved in this process. So what is happening? First, for the heat of combustion of graphite to give pure carbon monoxide, what will be the reaction? See, graphite. They react with half moles of oxygen. Okay, so for its combustion will produce C and O, that is carbon monoxide gas. Okay, so it is called delta H2. Now, if this carbon in its graphite form reacts with oxygen gas, then what will happen? It will form CO2 gas. And let us say the enthalpy for this reaction is delta H1. Now, this CO, that is carbon monoxide, if it reacts with half mole of oxygen gas, what will it form? CO2 gas, which is nothing but this one. So we can write it like this. We can simply write it like. Yes. If we provide half mole of O2 gas, it will form this carbon monoxide gas. So here, If this is the case, I have told you in earlier that enthalpy change for a reaction using this law, we know that enthalpy change of reaction is same if it's either it follows a single step or a multiple step, providing the initial and final state are same. So here initial state is C and final state is CO2. Okay, so here it is occurring in single step and here it is going through two steps. Okay, so if we calculate the enthalpy for this reaction, then that is delta H1, and enthalpy for this reaction, that is delta H2 plus delta H3. Then your delta H2 plus delta H3 will be equal to your delta H1, which is what is your His law. Okay, so according to His law, your delta H1 will be equal to delta H2 plus delta H3, because for this process your enthalpy change will be delta H2 plus delta H3, and this will be equal to your enthalpy change in the single step, that is delta H1. So if this is the case, we know what is delta H1, C plus O2 giving CO2. So it is already written over here, that is oxidation of graphite to CO2. It is given as minus 393.5 kilo. So we already know this. So we know the value of H1. So delta H1 is no. Now delta H2. Delta H2 is what we have to calculate, which is your rate of combustion of graphite to produce CO2. Yeah. Rate of combustion of graphite to produce to form CO2. So this is what we have to calculate, and it is difficult to measure. So this is not. Let us say it is. Now delta H3 is what? Reaction of carbon monoxide with oxygen to form carbon monoxide. Here it is written that the oxidation of carbon monoxide to carbon dioxide can be easily be measured, and it is minus 283.5 kilojoules. So here, if it is minus 283.5 kilojoules, that means we also know this value. So delta H3 is also known. So if we know two values, so we can easily calculate other value. So if you know this value and this value, you can easily calculate delta H2. So what will be your delta H2? Yeah. Delta H1 minus of delta H3. Okay. So your delta H2 will become equal to delta H1 minus delta H3, and delta H2 is nothing but your rate of combustion of graphite from carbon monoxide. That means we can easily calculate if we know these values, that is rate of combustion of carbon to carbon dioxide and carbon monoxide to carbon dioxide. Okay. So this can be calculated, and if you put these values, your delta H2 will become delta H1 is your this one, carbon to carbon dioxide. It is minus 393.5 kilo, and minus of delta H3. Delta H3 is this one, carbon monoxide to oxygen, which is minus 283.5, and this minus will become plus. So it will become plus of 283.5 kilo. Okay. So plus minus will be minus, and it will come out as, let me calculate it. So minus of 393.5 plus 283.5. It will come out as minus 110 kilos. Okay, so your delta H2, that is your rate of conversion for graphite to get CO, will be equal to minus 110 kilos. So this is what we can calculate using case. Right? So this was the application of this see the beauty of this. So we can easily calculate what is actually very difficult to use. Okay. So in this class, what we studied the application of the changing enthalpy. Okay. So first we studied how we can calculate the calorific value of food and fuels, and then we studied what actually is calorific value, which was nothing but the then your 1 gram of substance is one, and we calculate the heat producing calorie. Okay, so that we call as a calorific value. Then we studied the heat of solution, and after that we studied heat of neutralization. Okay, so and here in this case, this statement was very important that the heat of neutralization of the strong acid and strong base is minus 57.32 kilojoule, irrespective of the nature of acid and base. But this is important that the acid or base should be strong acid and a strong base. Okay, so this was what we studied in this slide. After that, we studied what is molar heat of fusion, molar heat of vaporization, and molar heat of sublimation. Okay, and the basic difference was what in molar heat of fusion, your solid was converting into liquid phase, and in case of vaporization, your liquid um, you are going from liquid state to gaseous state, and in case of sublimation, you were directly going from solid state to your gaseous state, that is your vapor state. Okay, so then we studied some examples. After that, we studied the heat of transition, which is the enthalpy change on going from one electrotropic form to another form. And then we studied the Haies law of constant quick summation, which says that whether a reaction follows a single state or multiple states, the enthalpy change of the reaction at constant volume and pressure will remain same, uh, providing that the initial and final states are same. Okay, so this is what we studied, and after that we studied the application of the Haies law, and we solved this problem where it was very difficult to measure the heat of combustion for uh, a particular molecule. So particular reaction. So the heat of combustion of a particular reaction was difficult to measure, and we measured it using the Haies law. Uh, okay, so this is what we have studied in this class. Okay, so I'll end this session now.